to this episode of Garage Science. Bob and I were just looking at our latest acquisition here. We just picked up at a yard sale. Isn't it a beaut? Every garage ought to have one of these. It says on here, Dr. Miller's Animal Marker and Pig Snouter. Now, who wouldn't want a handheld pig snouter? I mean, now I don't own any pigs, but I do cook myself bacon and eggs every now and then in the morning, and I could mark the bacon so nobody would take it. But I actually live with a bunch of vegetarians and they wouldn't take it anyway. But this is it's just a fun thing to have, okay? Unless you're a pig. But it's our introduction to simple machines. We're going to look at all 6 simple machines. We're going to look at the inclined plane family first, and then we're going to later look at the lever family. Now, to begin with, inclined plane, easy, they're everywhere. Flat surface on an incline. Okay, now, we use them to get things go down them. We use them to make things go up them. Okay? Pretty simple, right? They are simple, but in another way, they're very mathematically beautiful and pure. All simple machines, if you can understand an inclined plane, you can understand all the other simple machines too. And basically, why do we use machines? Well, supposedly they make our work easier. But what does that really mean? It has to do with the force I put in versus the force I get out in most cases, or it has to do with the distance I have to move versus the distance that the object moves and I'm trying to move, the resistance. With an inclined plane, it's pretty simple to see. I move an effort a certain distance using this inclined plane. What would happen if I didn't have the inclined plane? Well, that's the output. See? That's how far I'd have to move it if I didn't use an inclined plane. Put it in there. Now I use this. And it helps me. And you can have, I don't drive very straight at all. Maybe you ought to do it, Bob. The benefit from it, called the mechanical advantage, is just a ratio of how far I move something to how far the object would move if I didn't have the machine. My effort, the resistance. So let's start off by looking at a simple machine, the inclined plane. We'll do a little bit of math on that, and then we don't have to do it for any of the other ones. Before we jump into the individual 6 simple machines, let's look at something that's true for all simple machines. And that is the work you put in, your force through your distance, or in this case, your effort force through your effort distance, how far you moved, is exactly equal to the work you put out. Output force, the output distance, or in this case, the resistance force and the resistance distance. They always turn out to be the same. I find that fascinating. They're just always the same. That's okay. Somebody in the back row is going, what about friction? What about friction? What about friction? We're ignoring friction right now. Okay, we're just ignoring it. Pretend it doesn't exist like certain relatives, right, Bob? Okay, so it's true for all simple machines. There's another mathematical principle there that's called mechanical advantage. That's how many times that machine multiplies your force. I mean, after all, it must be a reason we use simple machines, and this is it. Mechanical advantage. You find it out by taking your effort distance, how far you move, how far does resistance move. Okay? All right. Now let's look at some individual machines. Let's just break the thing. Good idea. Here's our inclined plane. Got basic 4 parts. The effort distance, how far you're going to move. Your effort force, that's the push you put in. How far would the object move if you didn't even have the machine, just usually in a straight up position? And resistance force, what does it weigh? Well, an inclined plane is a flat sloped surface. So we got that pretty much squared away. Okay, here's the mathematics of why the heck we use them. Here we go. Say that's a meter high. This C is 2 meters, B is 5 meters, and A is 10 meters. So what's the advantage? Well, let's take a quick look. We said the work out equals the work in. Okay? I got them backwards, don't I? Ah! Yeah, they're backwards. Okay. Hold on a second. Just keep in mind, this works both ways. Everybody makes mistakes. I just seem to have made a habit of it today. All right, here we go. Got the right formula, got the right things written in. Life is good. So what you can see here is as the distance gets shorter, the force you have to put in gets larger. And the reverse of that is true. As the distance gets longer that you have to move, your effort distance, the force you use gets less. And that's why we say machines make work easier. What we really mean is we're using less effort force as we go farther. Now I can go the other way around too, that we put in more force, but then we're doing a machine that makes us want to make things go farther. Okay, we'll look at that when we look at levers. Okay, so now this is one wonderful thing about inclined planes, but there's an even better thing about inclined planes. Bob and I will show you. The best thing about inclines is going down them. Woohoo! The second machine we're going to look at in the inclined plane family is the wedge. And a wedge is a device that is thick at one end and tapers to a thin edge at the other. A wedge can be thought of as two inclined planes back to back that can move. So if you think about, there's our wedge. If I put a line down the middle here, somewhere near the middle, don't judge. Okay, see, two inclined planes back to back. Now, you put the force in here, you get the force out there. Again, you can figure out mechanical advantage. Okay. For instance, if you have this wedge, and this wedge, now they all have the same opening distance. Okay, they're all going to open at the same amount, but the effort distance here is, say, 1. This is 2 times whatever D is, and this is 3 times whatever D is. So this would have your greatest mechanical advantage. You're going to push it. It's going to take longer to get it in, but you use a lot less effort. So the longer and pointier it is, greater the mechanical advantage. That's why needles are easier to get stuck in you than, say, a railroad spike. Okay? So let's go outside and take a look at some wedges. Wedges appear on lots of hand tools. Very useful. Bob and I have come out here in the backyard to show you some uses of wedges. Now Bob here used our chainsaw to cut the piece of wood, and if you notice, each tooth on a chainsaw is an individual wedge, and it's just spinning around there, and you're putting a lot of input, the engine's putting the input power into it, and it's cutting into the wood. The wedges are being driven into the wood. So if he split it, if he cut it, I should take the time to split it to show you another wedge. So we're going to try that. We'll put on our protective gear here, make sure that we're doing safe science. All right, we'll get this wedge started in here. Okay, we'll give it a couple of little tippy taps here. And it falls over, which is about normal. We'll give it another one. Ooh. There you go. See? Practical use of the wedge. We'll see you inside. Thanks for setting that up, Bob. Bob, really? Seriously? Okay, we'll talk later. The third machine that is in the inclined plane family is the screw. Now you think of a screw as an inclined plane wrapped around a cylinder. The mechanical advantage is found this way. The finer the threads, the greater the mechanical advantage. Think of that spiral threads, okay? That's your effort distance. That's how far you've got to go, okay? And the height of the screw is the resistance distance. So if you're comparing effort distance, resistance distance, you're going to be going a lot farther than what it's going, but the finer the threads, the easier it is to turn in. We'll show you a couple examples. Some that don't involve, okay. I've made here 2 inclined planes. We're going to show you the relationship between inclined plane and screw. Both of these inclined planes have the same resistance distance or the same height. Now they vary in the effort distance. Well, if you take these and you roll them up, say around a rod like that, they turn out looking just like this. There's Q, all right, and there's Z. And you can see the difference in the threads. This one has much finer threads, these have thicker threads. This one have a much greater mechanical advantage. Longer effort distance, because remember, mechanical advantage is relationship between effort distance and the distance that the machine would go without, or how long we have to work without the machine at all. So you can see the difference there in threads. And we use threads when we think about screws and things like that. That's normally about fasteners, because before we had screws and bolts, all we had were nails. Just nails. Or rope, or rawhide, or I don't know, even before duct tape. We had nails. So when material science got to the point where they could make better metals and they could work the metals and make things like screws or spirals or threads, things really progressed. Look at all the things here that use threads to hold things together. Now that's not the only reason we use threads, but most of the time it is. And they're fascinating to us. You got little bolts like this, you got medium bolts like this, and you got big honking things like this. And they're all used to hold things together because it's a much better thing than a nail. We also use the threads for some other things. Let's say you want to drill a hole in something, okay? Well, years ago you used a thing like this, huh? Instead of those, you use this. You had to be Mr. Manly to drill a hole with this puppy, okay? But really when you look at it, if you look closely, you'll see there's a little tiny screw there that bit into the wood, and right behind it are wedges, the second member of the inclined plane family. And then you have the screw again to get rid of the wood chips. Isn't that amazing? They use all the simple machines, thing like this. Also, here's another machine that we just had laying around here, which is scary. Remember, don't judge. Okay? Let's say you wanted to jack something up. Hey, look, advertisement. Okay? This is a screw jack. Now, you got to be Mr. Manly to use one of these puppies too. This is how you would jack up, say, a barn or house or building or part of railroad, something like that, to get it to move, because we didn't have hydraulics. So they used the next best thing. They used a screw. See? It works. You just turn it like that, and up you go. Okay? Wouldn't that be a fun job? Okay? And you know what they did after that? They did this. They applied what they knew and made hydraulics. Huh? See? Good technology, but look at this. There's a little screw jack in there anyway to take up the space. Okay? Now to end with here, let me show you this. This is, I'll move these guys out of the way. This is an old canning jar. What in the world's that got to do with anything? Well, you know, this would have been like how Abe Lincoln would have preserved peaches or something. Put that in there. And that just clamps down on there. That was a rubber seal there. Improvement. Material science got better. We learned how to make glass like that. Put threads in this, made zinc lids like this. And there was a rubber thing in there too. And that just sealed down on there. And that's how you sealed your jars. And that about puts the lid on our study of the inclined plane family. They're ubiquitous, they're everywhere, they're underappreciated. So when you start looking around, you're going to see them everywhere now that you're used to them. All right, see you next episode. Oh, better watch that.